In this section, we'll be looking at horizontal transformations of functions. And so those transformations will affect the input or the inside of the function. So that'll affect the domain values. So I want you to think about the fact that if we have y equals f of x as our function, x is the input, and the domain tells us that the inputs x have to be between -2 and 8. So what happens when we change the input for the function? So for instance, in example 1a, our input changes to x minus 3. So instead of x being between -2 and 8, x minus 3 will have to be between -2 and 8. We can solve this inequality to find the domain of this related function by adding 3 to all three parts of this inequality. So -2 plus 3 is 1. In the middle, if we add 3, we just get x, and 8 plus 3 is 11. So the closed interval from 1 to 11, or including the endpoints, that is to say, is the domain of that new function. All right, let's take a look at f of 2x. This one also has a change in the input. The input is 2x. So 2x has to lie in between -2 and +8. Dividing all three parts by 2, we get -1 to 4 is the domain of the new function. In C, there's a lot going on in this function. There are some transformations, but the input remains x. So in this, there's no change in the input, and so there is no change in the domain. The domain of this one remains -2 to 8. In the next one, our input changes to -x. So x, or rather -x, has to lie between -2 and +8. And when you divide by -1 to solve for x, we're going to get 2. And remember that dividing by a negative in an inequality reverses the direction of the inequality symbols. And although that's an acceptable answer, I'm going to prefer to write my answer as -8 is less than or equal to x, which is less than or equal to +2, because then the least number appears on the left and the greatest number appears on the right, just the same way those numbers appear in order on the x-axis. All right, let's take a look at a couple others. There are multiple transformations going on in E, but the input is the only one that I'm worried about because we're dealing with domain. So 1/2 x plus 3 has to lie in between -2 and +8. There are a couple of different ways that we can solve this one. There are multiple steps. You could multiply through by 2 first to clear the fractions, or you could subtract 3 first, whichever you prefer. So let's subtract 3 first, and that'll give us -5 is less than or equal to 1/2 x, which is less than or equal to, and 8 minus 3 is +5. Now multiplying both sides of this inequality, or rather all three parts of the inequality, by 2, we get x is between -10 and +10. And last inequality, this one has an input change. The new input is 7 minus x, so that is what will have to lie in between -2 and +8. And remember that the 7 is positive and the x is negative, so we're going to subtract 7 to isolate the x, subtracting 7 and then dividing by -1 reverses the inequality. And then you're typically going to see that written as -1 is less than or equal to x, which is less than or equal to 9. All right, now that we've got the domains, the idea of change in domain taken care of, let's do some actual transformations. So here is a graph of y equals f of x. I've included it in the grid, and our job will be to graph y equals f of negative x. So if we think about the order of operations necessary to evaluate f of negative x, if we start with an x value, we'll have to take its opposite first, and then we will have to take f of that opposite value. All right, now what's really important that you understand is when we make this table of values, that it's these two columns here, negative x and f of negative x, that contain the points from the original function. In other words, those are our input values for the function and the output values of the function. Whatever you see in the input column, -4, if negative x is equal to that, then f of negative x is equal to f of -4, which would be -2. So I just picked that 1 point off of the graph. All right, now we're going to just pick the points on the graph that are really turning points, where the graph kind of changes direction or changes slope. And so we're going to skip by 2's. So when x is -2, f of negative x is -1. And if the input is 0, the output is -2. If the input is 2, the output is -4. And if the input is 4, the output is 0. So now I want to think about what it takes to go in one direction or the other. If I have an x value and I want the opposite of it, I just need to multiply by -1. If I go the other direction from the second column back to the first column, I'm going to divide by -1. In this case, it doesn't really make any difference because multiplying by -1 and dividing by -1 give you the same result. So what are we going to do? We're going to take the opposite of all of those values, +4, +2, 0, -2, and -4. Now let's remember that when we're graphing a related function, we have our x values and we have the y values, which are equal to f of -x. So the two columns that I highlighted are giving us those ordered pairs that we're going to graph on the function. Let me get rid of my stray marks on the graph, and we'll be graphing the point +4, -2, +2, -1, 0, -2, -2, -4, and -4, 0. So connecting those points together, we can see that we have a horizontal reflection or a reflection over the y-axis. All right, let's take a look at B. In B, our function is y equals f of 1/2 x. So our inputs are x, and then we have to half them first, and then take f of whatever that value is. The second two pair of columns are the parent function columns, so that's where our points go. If our input is -4, then the output is -2, and so on. We're just going to list those same ordered pairs that we did in the last example. That is the benefit to using the same function over and over again. We don't have to think about it so hard. And then I want you to think about what it takes to go from x, if we have an x value, to a 1/2 x value. We're multiplying by 1/2. And so if we're going in the other direction, we're going to divide by 1/2, which is equivalently multiplying by 2. So we're basically going to double all of those 1/2 x values to get the x value. So doubling, -8, -4, 0, 4, and 8. And again, the input column on the left, that's our x values, and the output column on the right, that's our y values. So now let's just graph those ordered pairs. -8, -2, -4, -1, 0, comma, negative 2. So far that's what we have. 4, comma, negative 4, and 8, comma, 0. So this one, we've performed a horizontal stretch. And these may be transformations that you recognize from your work in Algebra 2. All right, let's take a look at a couple other, one more simple transformation, and then we'll take a look at some unfamiliar ones. So y equals f of x minus 2. We'll have our x value, have to subtract 2 first, and then take f of that value. The points for the original function go in the x minus 2 and the f of x minus 2 column. So negative 4, negative 2, negative 2, negative 1, 0, negative 2, 2, negative 4, and 4, 0. If you think about going from the x column to the x minus 2 column, we would be subtracting 2. So if we're going the other direction, we'll have to add 2. So negative 4 plus 2 is negative 2. Negative 2 plus 2 is 0. 0 plus 2 is 2. 2 plus 2 is 4. 4 plus 2 is 6. Again, we are graphing the ordered pairs, input and output, the very first and last columns. So we have negative 2, comma, negative 2, 0, negative 1, 2, negative 2. That's what we have so far. 4, negative 4, and 6, 0. So this one was a translation 2 units to the right. And we can kind of get the idea about why you have to translate right, even though it says x minus 2. We're undoing that operation. We're adding 2 to the x values, which is why we head in the rightward direction. And so I think probably if you're doing a single transformation like these last 3 examples, I think maybe you could probably get away without actually making the table of values, although I do think the table of values prevents errors from happening. But I would recommend that if you're dealing with something like the next 2 examples, which are combined a couple of different transformations or an unfamiliar transformation, that you use the table of values approach. I want you to have lots of tools in your tool belt that you can use to graph a function. All right, we're going to stick with 3 columns, even though there's more than one operation to get from column 1 to column 2. We have to, but I think we can do this in our head, right? So our parent function points are going to go in the same 2 columns, the rightward columns. Negative 4, negative 2, negative 2, negative 1, 0, negative 2, 2, negative 4, and 4, 0. So now I want to think carefully about the operations required to get from x to 2x plus 4. If I go from x to 2x plus 4, number 1, I have to multiply times 2, and then secondly, add 4. So if I'm going in the opposite direction from 2x plus 4 back to x, I'm going to accomplish this by undoing those operations and undoing them in the reverse order. So I'm going to start with add 4. I can undo that by subtract 4. And I can undo times 2 by dividing by 2. So for each of those values that we see in the 2x plus 4 column, we're going to start by subtracting 4, and then we're going to divide by 2. So let's start at the bottom there with 4. 4 minus 4 is 0, divided by 2 is 0. Now let's move on to 2. 2 minus 4 is negative 2, divided by 2 is negative 1. And now let's go to 0. 0 minus 4 is negative 4, divided by 2 is negative 2. And now negative 2 minus 4 is negative 6, divided by 2 is negative 3. Negative 4 minus 4 is negative 8, divided by 2 is negative 4. And you can kind of tell that we've done the operations correctly because what you'll notice is if we've done all of them consistently, that where our 2x plus 4's, the values increased by 2's, our x's increased by 1's only. All right, let's graph our inputs and outputs to get the transform function. So we have negative 4 comma negative 2, negative 3 comma negative 1, negative 2, negative 2. So there's what we've got so far. Negative 1, negative 4, and 0, 0. So I think we can see a horizontal compression as well as a translation. All right, last example of this type, and this is an altogether new type of transformation. We have x. We'll have to take its absolute value before we take f of that value. Parent function points go in the last two columns. And now we want to think about the transformation that we're doing. So what I want you to think about for this one right here is, what if the absolute value of x is equal to 4? What can x be? And there are actually two possible answers here. X could be 4. X could also be negative 4. So that means we're actually going to have 2 points there. We're going to have 4, 0 and negative 4, 0. All right, moving on to the second point here. If the absolute value of x is equal to 2, then x can be plus or minus 2. If the absolute value of x is 0, then x is 0. This one only gives us one value. Now, what if the absolute value of x is negative 2? Well, actually, there is no x value that makes that true. There's no solution to that equation. So that one's not going to yield an x value for us. Same thing with the if the absolute value of x equals negative 4. That's not possible, so we can't get an x value from that one. All right, so this one's going to look a little bit different. So we have the point 4 comma 0, and we also have the point negative 4 comma 0. We have 2 comma negative 4, and we also have negative 2 comma negative 4. And then we also have 0 comma negative 2. So what you'll notice is that the right side of the graph stayed in exactly the same place. And if I asked you what happened to the left side of the graph, you might say it's not there any longer. What was the left side replaced with? A reflection of the right side. So this is a very different transformation from what you've seen before. All right, let's take a look at a more familiar function, one that's not a series of line segments. Let's take a look at g of x equals the square root of x. So for this function, we want to start with the smallest x value that we can take the square root of, which is 0. The square root of 0 is 0. Next, we have 1 is another value that will give us a whole number square root. The square root of 1 is 1. The next value that will give us a whole number is 4. The square root of 4 is 2. And let's go to 9. The square root of 9 is 3. That's going to give us basically what this parent function looks like. 0, 0, 1, 1, 4, 2, and 9, 3. And just pointing out, that really is the shape of a parabola. It's not a full parabola, it's only half of one, and it also sits sideways. but it is in fact the same shape as a parabola. Maybe in Algebra 2 you called that the hook. All right, now we're going to do a transformation on this one. So we'll use those same parent function points. And so we'll have to put our x values in, then 4 minus 1/2 x. And I'm actually going to backtrack here a little bit. Instead of doing 4 minus 1/2 x, I'm going to rewrite this as negative 1/2 x plus 4. Generally speaking, if we think of it as a multiplication first and then adding or subtracting something, that's going to make it easier to do the operations. And then last column is g of that value, which will be negative 1/2 x plus 4. All right, parent function points go in the second and third columns. And now let's think about those operations that happen when we go from x to negative 1/2 x plus 4 and then in reverse. So if I go from x to negative 1/2 x plus 4, I number 1 multiplied times negative 1/2, and then second add plus 4. So if I'm going from negative 1/2 x plus 4 back to x, I'm going to undo those operations in the reverse order. So we're going to start with minus 4, and then we're going to undo the times negative 1/2, which is times negative 2. All right, so let's start with 0. We're going to subtract 4, that's negative 4, and then times negative 2 is positive 8. And then 1 minus 4 is negative 3, times negative 2 is positive 6. And then 4 minus 4 is 0, times negative 2 is 0. 9 minus 4 is 5, times negative 2 is negative 10. Okay, it's really important that we do these correctly because 0, 1, 4, 9, they don't skip by the same amount each time, or they're not they don't have the same difference in between the values, so we have to check these very carefully. And we'll notice when we graph if something looks amiss. So we have the first and last columns, which give us our input and output values. So we have 8, 0, 6, 1, 0, 2, and negative 10, which doesn't quite fit on the graph, but I'm going to put it there anyway so we get a better shape. And we get a stretched and reflected and translated graph. So there are really 3 transformations that are going on there. All right, now let's take a look at a quick trig function. We have h of x is equal to cosine of x. So we have our x values, which are going to be our quadrantal angles, 0, 90, 180, 270, and 360. And let's think about our location on a circle at 0 degrees. And let's also think about a reference triangle. Any random reference triangle will do. What we want to make sure that we always think about is that the adjacent side is horizontal and the opposite side is vertical. So when we look at our location at 0 degrees, our horizontal coordinate is 1 or 2 or any other non-zero number, and the vertical coordinate is 0. What that means is opposite side is 0, but adjacent side is non-zero. And that's going to tell us when we're dealing with cosine, which is adjacent over hypotenuse, that the cosine is equal to 1. Now, if we get that first value figured out, I know we can do the rest of those easily from there. There's only one place to go from 1, and that's down. 1, 0, -1. Now back up, 0, 1. So when x is 0, the y is 1, 90, 0, 180, -1, 270, 0, and 360, 1. And that gives us our nice cosine sinusoidal shape. And of course, I'm just going to write this in another color. The graph continues on both sides to other cycles, but the red part is just the one primary cycle. All right, now let's take a look at y equals h of 3x minus 90, which would be cosine of 3x minus 90. So if we're thinking about our order of operations here, we have x, 3x minus 90, and h of 3x minus 90. Parent function points go in those second and third columns. And to get from x to 3x minus 90, we multiply by 3 first and then subtract 90. So to undo that, we're going to add 90 and then divide by 3. So let's take care of 0 first. Adding 90, that's 90, and dividing by 3, that is 30. Now on to 90. Adding 90, that's 180. Dividing by 3, that is 60. And I think by this point you can see there's a pattern here, right? The 3x minus 90 column is going by 90s. The x column is going to go by 30s. So 30, 60, 90, 120, and 150. So let's highlight our first and last columns. So we have 30 degrees, comma, 1. 60, 0, 90, -1, 120, 0, and 150, 1. So that's going to give us one cycle. Oh, that was a lousy drawing. Let me try that again. All right, and then I'm just going to continue drawing in more cycles to complete this. But and you don't have to use colors when you do this, but I think it's easier for you to see that I drew that one primary cycle first, and then I'm just kind of using the pattern here to draw some additional cycles. Okay, all right, now that's it. And I believe that's it for the lesson. We'll do some combined transformations in the final lesson for this unit.